Now, let us see the level shift PWM technique. Okay. So, we have covered the phase shift PWM and now we will see the level shift PWM. In level shift PWM, the carriers for each cell are identical. Okay. Normally, they are all identical. Some types of LSPWM exist with carriers non-identical, but let us start these carriers being all identical, but they are all vertically phase shifted or vertically shifted from one another. So, you have one carrier here, second carrier here, third carrier here, fourth carrier, like that. And that is why the term level shift comes, it is a level shift PWM. So, you can see, so these are the, for example, the carriers, okay, carrier 1, carrier 2, carrier 3, carrier 4, where the modulating waveform is shown like this, it is spanning like between minus 0.5 and plus 0.5, and the carriers are also like vertically shifted from one another. Okay. So, the fundamental voltage, like before in phase shift PWM, the fundamental voltage from each cell gets added up, because basically it is a series connection of edge bridges. So, the fundamental voltages by its connection itself will get added up. Now, let us take the same example as before, take the example of the 5 level CHB, and for a 5 level CHB we will need 4 carriers, okay, L minus 1, 4 carriers, and these are shown here with the different colored carriers in this diagram. So, what is the height of each carrier? The height of each carrier, if suppose the total height of the modulating or the reference wave is 1, then the height of each carrier is 1 by 4 or 1 by the total number of carriers used. So, it is 1 by 4 is equal to 0.25. So, which means that if this is the modulating waveform, its total height is 1, then the height of each carrier is 1 by 4 or 0.25. Basically, the idea is that the carrier should span the entire waveform. So, the waveform is here and the carriers are spanning throughout the waveform, okay, because ultimately you see we need to produce the sine wave, and if we do not have the pulse width modulation, we cannot produce the variable voltage which are part of the sine wave. The sine wave is continuously varying, and we need the pulse width modulation to mimic or to produce this varying sine wave. And so, if so the carriers must span. So, wherever the modulating wave is present, the carrier should also be present, so that we can replicate the varying nature of the sine wave. So, therefore, the carriers should span the entire height of the modulating waveform. And here we have shown a zoomed view of the carriers, where you can see that these 4 carriers here they are identical, okay, unlike the phase shift PWM. In phase shift PWM, these carriers were slightly phase shifted, but in level shift PWM we see that all these 4 carriers are perfectly exactly same, but they are vertically shifted from each other, okay, and that is why it is called level shift PWM. We would like to see exactly how the how the switches in the cells are switching using the level shift PWM technique. So, since this is a 5 level CHB, we have 2 such cells given by H1 and H2, and there are 4 such triangles which are given now the names triangle 1, 2, 3, 4 here. Triangle 1, 2, 3, 4, these are the 4 triangles. Now, this green waveform is the reference waveform, and what is the logic? So, if we see the cell H1 here, cell H1, the triangles which are to be used for cell H1 will be triangle 1 and triangle 3. These two triangles will be used to switch the 4 switches for cell H1, and for H2, that is this cell, for this lower edge bridge we will use V triangle 2 and V triangle 4. So, these two outer triangles we will use. If we had another cell H3, then we would have used 2 sets of more triangles, one here, another here, okay. And of course, the modulating wave will increase. So, what is the logic for switching the 4 switches inside H1? The logic is given here in this table. If the reference waveform is more than triangle 1, okay, the reference waveform is more than triangle 1, then we turn on S1, and of course, S1 and S2 are complementary. So, S2 is off. So, this is the logic for S1. If VRF is greater than V triangle 3, then S4 is on and S3 is off. Okay. So, of course, by seeing these two logic, you can understand that if VRF is here, for example, here, if VRF is in this position, then S1 is sometimes turning on and sometimes turning off, because VRF is sometimes more than triangle 1 and sometimes less than triangle 1. But VRF is always more than triangle 3. So, during this entire position, during this entire portion of the waveform, S4 will be completely turned on. So, this is how we get the switching status of all the 4 cells, all the 4 switches in the H bridge H1. Similarly, here also you can follow the same logic, and here you can see that when the reference waveform is here, then S1 is completely turned off, while S4 is sometimes turned on and sometimes turned off. Similarly, the same logic can be replicated for H2, which is shown here. If VRF is greater than V triangle 2, then S1 is on. If VRF is more than V triangle 4, then S4 is on. So, if here, when we are here during this part of the waveform, VRF is sometimes more and sometimes less than triangle 2, and hence S1 in H2 will be sometimes turning on and sometimes turning off. But for H1, during this part of the waveform, for H1, what will be the condition of the switches? We see that for H1, VRF is more than V triangle 1. So, the switch S1 in H1 during this portion of the waveform is completely turned on. So, we can see here that if I see switch S1, then here it is doing this on off, and then S1 completely is turned on here. Okay. S1 becomes completely turned on, this portion here, because S1 in H1, that is what I am saying, S1 in H1. So, this is S1 in H1. Here it will be sometimes turning on and off, that is doing the pulse width modulation, whereas during this portion of time VRF is more than V triangle 1, that is VRF, this portion is more than triangle 1. So, it has been completely turned on, and during this portion of time, S1 in H2 will be doing the pulse width modulation depending on the on off condition. So, this is the S1 in H2, okay. Whereas, in this portion S1 in H2 will be completely turned off. So, it will be turned off at the lower portion. So, you can see here how the voltage of the cells are getting cascaded and how they are supporting each other one over the other, and this way if there is one more cell, then there will be one more triangle here and one more triangle here, and then you will see that for one it is like this, and then the second one will be like this, the third one will be like this. In this way they cascade one over another. So, the level shift PWM. So, let us take an example just like the previous one. Assume that the carrier frequency is 20 kilohertz. Okay. Now, the harmonics at the output in level shift PWM will appear at 20 kilohertz, that is 400 times the fundamental. Now, the carrier frequency here is itself 20 kilohertz. So, note the difference between phase shift PWM and level shift PWM. There the triangular frequency was, or the carrier frequency was less, 2 kilohertz, because it was equal to the switching frequency of the device. Here the carrier frequency is 20 kilohertz, it is much higher. However, the average switching frequency will be still 2 kilohertz or same as phase shift PWM. We will see that. So, let us see that if the carrier frequency is 20 kilohertz, then the harmonics will reside at 400 times the fundamental, but the switching frequency of cells will vary. On an average, cells will switch at 20 kilohertz divided by 5, because there are 5 number of cells. So, it will come around 4 kilohertz, and on an average devices will switch at 4 kilohertz divided by 2, that is 2 kilohertz. Okay. So, the device switching frequency in both cases remain the same, but in phase shift PWM the carrier frequency is equal to the device switching frequency, and in level shift PWM the carrier frequency is equal to the effective output switching frequency. So, that is what this slide shows. So, let us take and see this example, that for example, we have 5 cell CHB and we are taking the level shift PWM strategy, and the output of each cell is shown here. So, for example, the output of cell 1 is something like what is shown here, output of cell 1. Okay. Why the output is looking like this? This is because see, as I have told you earlier, so this is the sine wave I am trying to produce like this one. So, cell 1 is kind of like taking the responsibility of producing one part of the waveform. So, cell 1, say for example, cell 1 is producing this, the waveform here. So, of course, it means that the cell 1 will do a pulse width modulation here or switching here and here, and the rest of the time it will be just turned on fully, and so that it can support the next cell. Okay. Similarly, at the negative side it will be like this and then fully like this, and then it will do the switching here. This is what is this waveform here. You can see this is the switching area, and then it is clamped, cell 1 is clamped, and then again the switching, same like this here. Cell 2 for example is taking this part of the waveform. So, it will be switching here and then it will subsequently get clamped, and this is what cell 2 is shown here. You see this part till this part it was. So, then means I will kind of like cell 2 sits over the top of cell 1 and subsequently cell 3 sits over the top of cell 1. So, in this way you can see, for example, cell 5 does not switch here, it is just 0, because it was waiting for cell 1, cell 2, cell 3, cell 4 to come up to that topmost region here, and then it is switching there. Okay. So, you can just pictorially see or visualize how these cells are stacking, how their waveforms are stacking up one over another. So, the harmonic spectrum, if you see, it is again similar. Okay. So, the pole voltage harmonics, again the output voltage is 4951 volt, and the fundamental is kind of 100%. There is a third harmonic and there is no other, there is triplet harmonics, third, ninth, 15th, there is no harmonics in between, and the first band exists at 400 times the fundamental, that is 20 kilohertz. Okay. So, the load phase voltage exactly like before, the harmonic sidebands exist around 400 here, and the triplet harmonics have disappeared. Triplet harmonics have disappeared here, and all harmonics at 400 times the fundamental. Line voltages also does not have the triplet harmonics anymore. The line voltage is √3 times the peak phase voltage magnitude. Now, when you see the level shift PWM, we find that the loss distribution is not same in all the cells. Conduction and switching losses are different. This is very easily understood from this waveform here. If you compare the output waveform of cell 1 and cell 5, you can very readily see that the losses of cell 1 and cell 4 are markedly different. For example, cell 1 has a switching loss here and a conduction loss here, because it is clamping the voltage there. So, there is a conduction loss, whereas cell 5 is not switching at all, it is 0 voltage here and there is a lot of switching here. So, level shift PWM causes an unequal distribution of losses in all the cells. You can see the cell 2, cell 3, cell 4, depending on the power factor also, the losses will get substantially different. Okay. So, but this is not the case with phase shift PWM. In phase shift PWM, the waveforms produced by each cell were almost identical. There was a slight phase shift, but that slight phase shift does not cause much change in the losses. But here the waveforms are dramatically different for each cell, and so the losses will substantially differ in terms of switching and conduction losses. And this is something which is a problem, because then because as we have said, cascaded edge bridge is built on the principle of modularity. So, we have a same heat sink design for all the cells. So, if one cell is heated up substantially, then its lifetime, or it will have a thermal overtrip, or its lifetime will be reduced. So, what to do? So, how to overcome this challenge? Because the pattern, we can see the pattern is present in front of us, and it is causing an unequal distribution of losses. So, what can be done? Remember, so the easy solution here is to rotate the patterns after few cycles. Rotate the patterns, what does it mean? You see here, cell 1 has this pattern of waveform and cell 5 has this pattern of waveform, but after a few cycles we can interchange their pattern. For example, cell 5 can be asked to produce this waveform and cell 1 can be asked to produce this waveform. It does not matter how their patterns are getting interchanged, because ultimately the output voltage does not get changed, because it is a series connection of cells. So, if I ask cell 5, to produce this waveform after say 1 second, and if I ask cell 1 to produce this waveform keeping cell 2, cell 3, cell 4 as same, for example, then the output voltage will remain same as before. Okay. But what will happen? The loss distribution, the division of losses, what was happening in cell 1 and cell 5 will now get interchanged. So, if we go on doing this rotation of pattern, say I ask cell 1 to take this pattern for 1 second, and then after 1 second I ask cell 1 to take this pattern, after 1 second I ask cell 1 to take this pattern and then this pattern and then this pattern, then over say 5 seconds I have asked cell 1 to go through all these patterns, so that the loss distribution becomes same for all the cells. So, in this way, by doing this rotation of the pattern or rotation of cells, we can ensure that the loss distribution in all the cells over a span of time becomes almost equal. Okay. This is what we have seen, that the loss distribution is same, not same in all the cells, but by rotation of the switching pattern we can make the losses almost same. There is one more thing, that one more feature of LSPWM which is interesting, is that instead of having 4 or 5 carriers, we can also have a single carrier implementation in level shift PWM. So, which you can see here, single carrier implementation. Why this single carrier implementation? See, these carriers, as I had earlier shown you, that for example, if there was a modulating waveform like this and there were like 4 carriers, we had seen example few minutes back, there were 4 carriers. Now, this 4 carriers, instead of using 4 carriers, we can use only 1 carrier, okay, like this one here. This is the only a single carrier which can take care of this modulating waveform. Why this single carrier is useful is, particularly it is useful in case of when we are working with DSPs, because DSPs, these carriers are generated in DSPs using counters. Okay. Up down counter will create a sawtooth waveform, no sorry, the triangular waveform, and only a up counter or only a down counter will create a sawtooth waveform. So, the counter goes on incrementing on every clock cycle of the DSP. The DSP has a limited number of counters. Okay. say modern DSPs are actually having a lot of counters. Modern DSPs can have 6 independent counters, but earlier days they had only one counter, for example, one or maybe 3 counters. So, it was useful to have this the implementation of LSPWM using only one carrier. Then the one counter of the DSP was good enough to do the LSPWM. So, when we use a single carrier, then what we do is we have to bring the whole modulating waveform inside one carrier, and this is shown here, this middle waveform. So, if we have this waveform, if I draw the carrier, say if I draw the carrier, for example, this is the lowest carrier, okay. This is the lowest carrier. Right. So, whenever, so if I want to implement, these are the 4 carriers, here there is the second carrier, third carrier and then the fourth carrier, not shown here. So, we are not going to use these 4 carriers, but instead we will be using a single carrier. Okay. So, if I have to do it, what I have to do? I have to bring the modulating waveform inside the carrier. So, how do I bring that? So, wherever the modulating waveform is crossing the carrier, we actually bring it inside the carrier by doing a shift. Okay. So, for example, see this is the modulating waveform and we will bring it inside one carrier. So, the modulating waveform is actually crossing the boundary of the lowermost carrier at these 2 points. So, if I have to bring it down, okay, so whenever it is going up here, I will push it down here and bring it inside the carrier, and keeping in mind that I have done a single push in this case. So, I have pushed it down. So, this you see this is the waveform here, and I have done a push down and it is bringing inside one carrier, because I want to implement the whole logic using a single carrier from the DSP. So, I have pushed it down and kept in mind that one push or one level shift has been done. Ideally, it would have been done by the second carrier, but since I do not have the second carrier, I am actually pushing, or I am bringing the modulating waveform inside the green carrier, which I have shown here. So, I am pushing it down. So, there is one shift. So, with one shift I have, so this waveform goes like this, and that is why this waveform goes like this, which is here shown. So, when it crosses the second carrier, so this is the boundary of the second carrier, and then we go to the third carrier. So, then I have to do 2 shifts or 2 pushes down. So, from there, this part of the waveform here, I will push it down inside the green one, and that is what this is doing here, 2 shifts. This part of the waveform is obtained by, this is basically this part, 2 shifts down, and the last part is where this part where the fourth carrier resides. Here is the fourth carrier resides. Here is the fourth carrier. So, the whole part of this waveform whole part of it, this part here will be fully pushed down inside the green one. That is what this push has done. This is the shifted waveform. Okay. So, I have pushed this whole thing down, so that now this is the new modulating waveform, and this modulating waveform will be compared with the carrier like this, which is this carrier here. Okay. So, the new modulating waveform is like this here. like this. So, then with this shifting or with this pushing of the carrier with the pushing of the modulating waveform, it is possible to bring the modulating waveform inside one carrier and helps in the implementation with DSP. Now, there are as I told you, there are some other types of level shift PWM techniques. Whatever we have talked about is called the phase disposition PWM, level shift PWM, which is this one here, okay, on the leftmost side, and this one you see all these carriers are identical, but they are just vertically phase shifted. Okay. There are other techniques also, like phase opposition disposition PWM, where you see these three carriers are identical, but vertically phase shifted, but these three lower ones are 180 degree phase shifted to the top ones. This one, this one, this one, these are 180 degree phase shifted to the top ones. Then there is also something called as alternate phase opposition disposition. So, these two carriers, alternate carriers, are 180 degree shifted like this. Okay. So, there are some more techniques also, and all these techniques have very similar harmonic performances, but as regarding, so there will be some minor changes in the ripples because of this different techniques, and sometimes they are useful, but we will stick to the phase disposition PWM, level shifted PWM in this course. Now, this is the last thing, how do we measure these harmonics? The measurement of harmonics is, or how do we quantify the harmonics? The harmonics are quantified by total harmonic distortion, THD. And so, what is THD? THD is the ratio of the RMS value of all the harmonic components to the RMS value of the fundamental. So, this is the definition of THD. So, you see the contribution of all the harmonics divided by the contribution of the fundamental. Okay. So, this is what expanded is this here. Now, although THD is an important parameter for voltage source converters, but it is not the most accurate depiction of harmonics. Why? Because the position of harmonics are also very important in voltage source converters, okay, apart from the contribution of the harmonics. So, for example, suppose I have a voltage source converter and I have PWM techniques. In one PWM technique, the output voltage, so this is the fundamental, and these are the some harmonics which I have produced, and this is say around 5th, 7th, these harmonics which I have produced here, and this is the fundamental. Okay. In another PWM technique, say this is the fundamental, same as before I have produced, but I have produced some harmonics here which is say at 1 kilohertz, or like about not 1 kilohertz, I will say around 30th harmonics, around 30th for example, but the amplitude of these harmonics are more than the amplitude of this one. Okay. If you now do the THD, okay, if you now do the THD analysis of this, you will see that THD is more here and THD is less here. Okay. THD is more because the 30th harmonics, the amplitude of those harmonics are much higher, whereas the THD is less because these are harmonics having less amplitude, although they are very close to the fundamental. In the second case, there is no harmonic which is close to the fundamental. Now, if you go by the definition of THD, of course, we want the THD to be as less as possible, then we are close to the fundamental. Harmonic contribution is less, if THD is less, the harmonic contribution is less, whereas if THD is more, the harmonic contribution is more. So, we will say okay, let us choose this one, but actually this is not good, because the lower harmonics, the 5th, 7th harmonics, these are more detrimental, okay. These are more problematic. For example, 5th harmonic, 7th harmonic causes 6th harmonic torque pulsation in the induction motor. Okay. So, this is never a good idea, because although the amplitude of 5th and 7th are small, but they are very close to the fundamental, and this closeness is something which must be avoided. In the second case, we have harmonics around 30th, and they can be relatively easier, they are easier to filter out by choosing a cutoff frequency, whereas for 5th and 7th it is very difficult to filter them out, or we need a very big filter. So, this 30th harmonics are relatively easier to filter out. So, therefore, this harmonic spectrum, the converter which produces voltage and whose harmonic spectrum is like this is the one which must be chosen, and this should be avoided, this should never be used, okay, or as far as possible try to be avoided. This must be avoided, this one, and this is better. So, therefore, THD is not an accurate depiction of harmonics from voltage source converter. Instead, we use weighted THD. It is a more suitable, where the weight of the harmonics have a role to play, that is the position of the harmonics. Okay. So, therefore, the higher it goes, lesser is the contribution. Okay. So, if H is high, then the contribution of that harmonics goes down, because it can be easily filtered out, for example, by the inductance of the motor. So, weighted THD is actually a more suitable description. So, when you compare voltage source converters in terms of harmonic performance, weighted THD is a more suitable expression. A 3-phase cascaded edge bridge converter having 4 number of cells in each phase of the converter. Okay, there are 4 cells. So, the converter is operated using phase shifted PWM technique with carrier frequency of 4 kilohertz, fundamental frequency 50 hertz, and the DC link is equal to 1000 volt. The question is the switching frequency of each device in the converter. Okay. So, inside the device, as we have covered in the theory, device switching frequency is same as the carrier frequency, right. We have seen that inside the cell, the carrier frequency is equal to the device switching frequency. So, if the carrier frequency is 4 kilohertz, then the device switching frequency is 4 kilohertz. Okay. The next question is the first band of switching frequency harmonics at the output voltage of each cell. So, each cell is a full bridge, and the first band of switching frequency harmonics from the cell output voltage from each cell will be double the switching frequency harmonics of the devices or of each leg. So, each leg is switching at 4 kilohertz, but when you see the cell output voltage, you will see that the output voltage has the first band of harmonics at 2 times of 4 kilohertz, that is 2 Fs, and this will be 8 kilohertz. Okay. Now, the first band of switching frequency harmonic at the output pole voltage will be 8 times 8 kilohertz we have obtained from one cell, and there are 4 number of cells. So, therefore, this will be 32 kilohertz. Okay. And the required phase shift between the carriers, this we have also covered in the theory, which will be equal to 360 divided by 2 times n, that is 360 divided by 8, which is 45 degree. So, here you observe that the device switching frequency is 4 kilohertz, but the overall output voltage switching frequency harmonic, the first band is at 32 kilohertz. So, it has been shifted by 8 times because of phase shift PWM. Now, if it is operated using level shifted PWM technique with the carrier frequency as 4 kilohertz. So, we have seen in level shift PWM there are all carriers here, and each carrier is at 4 kilohertz, okay, something like this. This frequency here is 4 kilohertz. So, the sine wave is somewhere here. So, then what frequency will the first band of switching frequency at the output pole voltage reside? Okay. The first band of switching frequency harmonics at the output voltage will be at 4 kilohertz. Okay. So, your carrier is 4 kilohertz and the first band of switching frequency harmonics at the output voltage will be also at 4 kilohertz. The next question is average device switching frequency. So, you can see from the waveform itself the device is switching only here and here, for example, and some devices are switching here and here. So, the device switching frequency is much lesser than the carrier frequency. In fact, it is carrier frequency divided by 2 into n. So, 4 kilohertz by 8, that is 500 hertz. Okay. So, if you see here, it is the same thing. Okay. Here, if you increase this 500 hertz to the previous value, that is 8 times to phase shift PWM. So, if this you increase to 4 kilohertz, same like phase shifted PWM, this will also increase to 32 kilohertz. Okay. So, it is comparable, phase shift PWM and level shift PWM is comparable. Of course, level shift PWM has slightly better harmonic performance, particularly when you have lesser number of carriers.